In this example, I want to discuss how to deal with the constant that will be standing in front of the logarithm when you want to differentiate the function that has logarithm. What I mean here, even though of course you can perform quotient rule using u over v and it will take you through the long process, we usually don't recommend using this method, just too long. So maybe consider rewriting the function as 5 natural log of x squared plus 4 raised to the negative 1. Now here's the question from students. Why I cannot write down this as a natural log of x squared plus 4 and everything raised to the negative 5, and then just perform chain rule 3 times and the problem will be over. You will see that the answer will not match with the answer you got if you used quotient rule. This is wrong because you're confusing a formula where you have natural log of the input, that's called t, to the 5, that indeed gives you 5 natural log of t. That's one of the laws of logs. Laws of logs. And usually what I will have on the right hand side is easier to differentiate. So that's what usually we do. We use laws of logs to get rid of this exponent. Basically put it down or multiply by that constant in front of the log. However, you are confusing with the situation when natural log of t is raised to the 5 outside. Then it's not the same and you cannot claim that it's going to be 5 natural log of t. What is the difference? The difference is which part of the function is raised to the 5th power. Laws of logs works only for the input that raised to the 5th power. And I like to explain in my classes that all properties of logs allows you to slow down the function. This is exponential function here located in the input. Log can slow it down by taking this 5 out of the polynomial, well, this is actually polynomial here, and putting it down and creating just a product of a function and a constant. But it doesn't work when the whole log is raised to the 5th power. Then you cannot do the same thing because now output is raised to the 5th power. The difference also can be shown as t times t times t times t times t 5 times versus log t times log t times log t times log t times 1, 2, 3, 4, 5 log t. That's not the same thing. So use laws of logs for this case. When you have complicated situation with the input, then log helps you to simplify the situation. But you cannot do the same thing when you have many logs, repeat it, multiply it. So this is just a side note which will help you to avoid this mistake. That means I will use this original form here where I have 5 times log raised to the negative 1 and I will differentiate this part. Let's do it. Negative 1. F prime of x will be negative 1 goes down, so it becomes negative 5. Natural log x squared plus 4, everything raised to the negative 2. Don't forget to decrease the exponent by 1. Times, chain rule says now we can look inside and differentiate the function inside. I see log inside. Derivative of log is 1 over everything inside, x squared to the 4 times. Now chain rule tells me look deeper inside and differentiate the function inside. Now I see that inside of the log there is x squared plus 4 Derivative of that is 2x. This can be simplified to, let's put everything we have as a product to the numerator, -5 and 2x, and everything you have with a negative exponent or in denominator, let's put it in denominator. So it's going to be a huge fraction. -5 times 2 is -10, -10x at the top, natural log of x squared plus 4, everything raised to the second power, times x squared plus 4. This piece showed up from differentiating log. Derivative of log of u is 1 over u. And this is the answer. Again, try yourself at home if you want. Use the original function and differentiate it using quotient rule, and you will see that the answer will be the same, but it will take you longer. Versus rewriting it, the function with a negative exponent, and using chain rule twice, 1 and 2. Makes it faster, but then make sure you don't make a mistake with the constant 5 in front of the function.